everybody, and welcome back. We're almost done the grade 7 Gauss paper from the year 2000. We're on to question number 24. So after this video, we're just going to have the final question, question 25, left to take a look at. But first, as I say, we got to go through question 24. So let's have a look at that. All right. So 12 points are marked on a rectangular grid. I'm guessing this is the grid over here, because it looks like these hexagons have something else to do with question 25. So 12 points are marked on a rectangular grid as shown. How many squares can be formed by joining 4 of these points? Okay. Now with a question like this, I would be tempted to guess, and I would guess 13. So before we actually solve the problem, let me explain why I would guess and why I would guess 13, and that's only if I didn't have time. The way this question appears to be worded, it's just a find the squares inside this little diagram. And so maybe you've seen something like that before, find the number of triangles in this diagram or find the number of squares or whatever. With a question like this, it's really hard to tell when you're done, when you've stopped finding squares. It's very difficult. So with that in mind, you could get 9 squares out here, but maybe there's 11 in here and you just can't see the right number. Okay? So unless there happens to be a nice, quick, clever way of counting the squares, which sometimes there isn't, sometimes there is, then you're never going to quite know if you're done. But we know that there can be at most 13. So if you were ever able to count 13, you would definitely know you're done. You have to take into account when you're doing these questions, and keep in mind the fact that there are multiple choice answers. Sometimes solving a question just means ruling out the other possibilities. Is that the case for this question? I don't know. I haven't actually tried it yet. But if it were a time crunch, if I just didn't quite know the answer, if I had counted some of them but I couldn't find others, but I thought I hadn't been quite exhaustive, I would just say, okay, I'll just guess the highest number. That's usually what I would do if I don't have time. But we have the time in this video, so we're going to see if we can find a way to count these, and we're going to see if we can find the answer. Okay. So let's draw ourselves the grid on our piece of paper, and we're going to need an extra piece right now. Okay, I'm going to draw the grid with some rather bold colors. Let's go with the red. I'm going to draw it big because I'm likely going to be marking it up with stuff. Alright, so that's our grid. It's nice and big. And so immediately I can see things like, oh, well, here's a square. And here's a square. And here's a square in here. And here's a square. And here's a square. So I've got 5 squares already. Okay? But at least they say that there's 6. So we got to start thinking about other squares. And we can hem and haw and, okay, well, what if I connect this one all the way down to here, and then I form a, oh, wait, I don't have the dot here. There's no phantom dot over here to make a square this way. But thinking larger squares definitely helps. And if we were to take a look at the diagram on its slightly rotated on the side, so we have those 5. Right now we're just exploring the problem. If I were to rotate it slightly, I would get something like this. And if I do that, well, I can see that this right here is going to be a square. And then I'll get this is a square, and this is a square, and this is a square. So none of these are the same as my previous squares, so now I have 4 extra squares, so at least 9. And that's useful information, it really is. And so I encourage you with a question like this, with a nice little diagram, a nice little visual thing, to, when you've got it on a piece of paper, if you're trying this contest out in real life, you can move the paper around, look at things from different angles, try and draw the picture yourself on a scrap piece of paper, move it. I mean, this is a 2-dimensional diagram. If it were a 3D question, you could always like flip and fold and whatever you want on your scrap paper. Try not to mutilate the contest booklet, of course, but you can always shift that around and look at things from different angles. And certainly that's how we found these extra 4 squares. Ruling out A6 and B7, so we're at least C9 or perhaps D11 or E13. But moving them around certainly gives us a nice little breakthrough. But we want to know, okay, that's great, there are those squares, but are there any others hidden in here? Okay? And that's what we're going to try and figure out. And if we can't find a way, that's okay. We could always say, well, 9's it, that's it, we're going to finish. Or we could follow my suggestion and just guess 13. But let's see if we can use a little mathematics here. It's the grade 7 Gauss, and I find up till the Pascal, and maybe even the Cayley, every once in a while there's a question where it's just, you got to guess, and guess and check, sort of. Not guess on your final answer, but you just have to stare at a diagram hard enough and find all the things that they want. Or just use your calculator and guess and check to find the right sum. Every once in a while there's a question like that. They're not poorly designed because they're not overused, they're interesting little quirks. Sometimes the best problem-solving method is guess and check. But let's see if we can find something else. So let's consider just a square. It could be one of the ones we already found, or it could be one that's hidden in there that we can't even see. Okay? So all the side lengths are going to be equal for a square. So what are the possible side lengths? Okay, well we already saw we could have a side length of 1. And then we saw you could go over 1 and up 1, and that gave a side length of square root of 1 squared plus 1 squared equals square root 2. So we've already found all the squares whose side lengths are 1 and all the squares whose side lengths are square root of 2. Are there other possible side lengths? Well, what if we went, starting here, we went up 1 and over 2? So that'd be square root of 1 squared plus 2 squared, so square root of 5. Okay, there's other possible things we could do. We could go up 2 and over 2. So that's a square root of 8. And we're starting to run out of space because, remember, we'll notice that we can only go 3 in any given direction, and that's at best. So the last thing we can possibly do, I mean, here's an up 2 and over 2. That's fine. But we can't go up 3 and over 2. We can only go up 3 and over 1. And that gives us 1 squared plus 3 squared, so square root of 10. So these are our only possible side lengths. We've narrowed down what the squares can look like. Now, this might have helped us, it might not. We're just experimenting with the question at this point. But we could now take a look at our diagram and see, okay, from this dot, can we go up 2 and over 2 when we get to this dot, and then does that form a square anywhere? So that sort of stuff. That's what we're looking for here. So, if we were to take make a little chart, so side length 1, so we'll put the squares over here, and we'll highlight all our squares. So we already saw all the ones for side length 1. Doesn't take too long to realize that this is going to be all of them. 1, 2, 3, 4, 5. And we took a look at side length 2 as well. Sorry, not side length 2, side length root 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So to get to side length root 2, I need to go up 1 and over 1. So over 1. So there was 1. Can I go up 1 and over 1 for this one? Yes, I can. Does that form a square? It does. Okay, and then this one down here. And this one down here. And we can check pretty quickly that this is all that we're going to have. And we can go up 1 and over 1 here, but there's no dots to match up. So it's going to be 1, 2, 3, 4 of these guys. So these are the 9 that we already had accounted for now. How about square root of 5? So that's up 1 and over 2. Okay, well let's pick a dot. So here's this dot, up 1 over 2. So can we then go over 1 and take down 1? Well, yeah, we got this here, and then this would match up with here. And we have ourselves a square. How about one of these middle dots? Here's up 1 and over 2. But there's going to be no extra dots down here to complete one for this guy right here. Okay, well let's stick to the outside. How about up 1 and over 1 here, here, and here. So we'll have 1, and then we'll have 2. And turns out those are the only ones that will have a side length of root 5. And that's okay. How about root 8 and then root 10 as well? 2, 3, 4, 5, 6, 7, 8. So up 1 and over 2. If I start at this middle dot here, or any one of these 4 middle dots, up 1 over 2, there's no dot there. So it can't be anywhere in the middle here. How about one of the outside dots? So I could go up 1 over 2. I could do that over there. But there's no dots down here, and there's not enough dots up here. And we would have to go up 1 and over 2, and then have to be a dot over here. So there aren't going to be any that work for root 8. Now you might think that this process is taking a little longer than actually trying to find everything just by looking at it. And you're right. If you were to do a guess and check and just look at the diagram, you would probably come up with the right number of squares. But we're going to know that there are no more squares when we do this. Now, if you look at the diagram and you manage to find 13, as I said before, then you're done. That's it. You know you can't get any more because they don't give you the option to have any more. But this way, we're going through all the possible side lengths. We're going through it very rigorously, sort of case-by-case work. We're finding out all the squares. So, this one's 0. Now, for this one, we need to go up 3 and over 1. When we do that, we say, okay, well, then it would have to be a square over here. So that's no. Or a square over like this. That's a no. And that's for one of the outside spots. What about the inside dots? Well, there's no way we can go up 3 and over 1 for any of the inner dots. It's going to be 0 as well. So we have 5 from the first one, 4 from the second case, and 2 from the last case. That's 11. So we don't need to guess 13. We actually have an actual answer, and that's going to be D. So it turned out my initial guess was wrong. I still stand by my reasoning as to why that would be my guess. But now we have, so if you were to do this by hand, you would possibly figure out at least 9. You'd probably figure out 11. But we used math to say, yes, there's 11, but we know there's not going to be any more. And that's the big advantage of doing question 24 this way. Now, if you strat for time, just eyeball it, and you can write down however many you see. That's a good way to do it. My strategy of just guessing 13, because that's the most, is certainly valid. It didn't work out this time, but it does work out in other cases. And yeah, but sitting down, thinking about it with case-by-case work with mathematics, D11, and we're pretty confident in that. So that's the second to last question, the penultimate question. We're on to question 25 in the next video, and I will see you guys there. Thank you so much for watching.